let's take a look at something we had looked at before. So we saw this last time, right? Electromagnetic radiation, sinusoidal electromagnetic radiation, propagating to the right. Okay, so we said that that's possible because it satisfies Maxwell's equations. Now, based on what we've talked about, how do you get sinusoidal electromagnetic radiation in the first place? What do you need to have happen? A vibrating charge, right? If you have electromagnetic radiation created by sinusoidally oscillating, or if the radiation is sinusoidal, and we know the radiation is caused by accelerated charges, then you must have sinusoidally oscillating charges. Okay. Oh, by the way, before we go too far into this here, we found. Let's go back to this example for just a quick second. We found that the radiative field, when it reaches this point, will be pointing that way. What's going to be the direction of the magnetic radiative field? Out. Why out? The cross product gives us the direction of propagation, right? We know it's moving to the right. E cross B, direction of E cross the direction of B gives us the direction of propagation, and we know it's coming from the charge, right? So we know the direction of B, and how do we get the magnitude of B? If we know this is the magnitude of the radiative electric field, how do I get B radiative? What was the relationship? Over C, right? B rad is equal to E radiative divided by the speed of light. Okay, so if you need to find the radiative component, you can do that easily because once you know the direction of propagation, you know the magnitude of the electric field, you can easily figure out the direction of the magnetic field and its magnitude as well. Okay. Well, you've already done that, right? You've already done that. So it doesn't matter. Once you know that the electron has produced this direction of E radiative, okay, then it's good. You have to have this magnetic field. If it had been a proton, okay, let's say it was a positive charge, then E rad would be down, and B rad would have to point into, right, to get you the same direction of propagation because you know it's coming from that charge. Okay, so sinusoidal radiation means you have to have sinusoidally oscillating charge, right? Because if we have a charge, let's just look at say you have some charge that's oscillating, okay, back and forth. And you know it's oscillating up and down, so its y position is going to be some amplitude times the sine of some function omega t, right? And you can say, okay, well then the velocity of it is going to be the derivative of that. We get a derivative of the sine is cosine, derivative of omega t is omega t. And then you take the derivative again to get the acceleration, right? So a sub y is going to be dy squared dt squared, or d squared y dt squared. And so you get the amplitude. Derivative of cosine is negative sine. We have an omega squared sine omega t. So the acceleration function is going to have a sine in it, and therefore the radiation itself, based on the formula we just saw, is going to have a sinusoidal oscillation in it as well. How do you get charges to oscillate sinusoidally? How can you have charges move back and forth? An oscillating electric field, right? Where can we see oscillating electric fields? I'll give you a hint. Just about everything in this room that has power associated with it. AC power, right? So if you have an alternating current, which we haven't really talked about, but it's basically the same mechanism to get charges to move in a wire, for example. If you have a wire and you have an electric field in here, well, that electric field is going to cause charges to move, or the mobile electron C in the wire to move in the other direction. But you might have an electric field that is some magnitude, again, times the sine of some function, some sine function. And so the acceleration of these charges is going to be sinusoidal as well, some amplitude times the sine of omega t, because the force is just Q times E. Okay, so if your field is oscillating sinusoidally, the force is going to oscillate sinusoidally, the acceleration is going to oscillate sinusoidally. We have what's called an alternating current. So let's come back to this thing that we showed a while ago. And we said if we plug this thing in here, and I bring this is just a light bulb connected to two wires via alligator clips, just copper wires that are insulated. And I bring it near this device, and the light bulb lights up. And if I turn it this way, it actually goes out. So if I bring it over here, it actually goes out. Can we now at least qualitatively say what's going on here? Any ideas? Yes, that's a good answer. Okay, so what possible ideas could we have? First of all, what's going on? What is this thing? This is an antenna. What do we have in it? We've got a metal rod here, and what's going on inside? We have an oscillating current, right? We have an alternating current, which is causing the electrons in the metal to do what? Okay, well, they're going to radiate because they're doing what? Oscillating, and so they're accelerating, right? They're accelerating in what direction? Up and down? How's this thing oriented here? Which way are the charges going to move? Yeah, back and forth, right? Okay, you're having a current that's being applied, or an electric field that's being applied, and that field is pointing in one direction, so the electrons in the bar accelerate in one direction, and then it flips, and so they accelerate in the other direction. And so you have charges that are accelerating either that way or that way, right? So, say again? Do they ever collide? Well, it's the entire the entire mobile electron C, right? Well, okay, so do we have internal collisions? Well, it's the same. What we really have is this thing's going to heat up for the same reason that a light bulb or any other thing with current passing through it heats up. The collisions are more occurring with the electrons, with the mobile cores, right? The positively charged atoms or ionic cores that are left over in the lattice. Electron-electron collision, we don't really model that. I mean, that doesn't really fit into the model because it's treated more as almost everything's happening instantaneously. Okay, because if you change, you got to have a change in some charge distribution somewhere that changes the electric field everywhere in the circuit. And it's one of these feedback mechanisms like we talked about when we were dealing with circuits, right, where it propagates throughout the entire circuit at the speed of light, and the electric field changes almost instantaneously. Okay, so pretty much everywhere the electric field is changing instantaneously according to some sinusoidal function. And then because the electric force is just proportional to that alternating electric field, the charges are all going to just basically oscillate back and forth the same way as the field is oscillating. Okay, but there are collisions with the lattice going on. Yeah, in some models you can treat it as sort of like a fluid, or a gas. An electron C is treated like an electron fluid or an electron gas that's all kind of moving, oscillating together. Okay. Okay. So you have oscillate. Let's draw this. Here's our antenna here, connected to this power supply. And we have electrons. Let me draw it more draw it thicker so we can actually draw the electrons inside that are either accelerating that way or accelerating that way. Okay. So here's my detector, and I bring it to an observation location in front of this thing. So I'm out here, right? And this is my wire connected to the light bulb. And the bulb lights up. So what's happening? Charges are accelerating, and therefore doing what? Emitting electromagnetic radiation. In where? In what directions? Okay, out. All directions. All directions except what? The line of the acceleration, right? The line of the acceleration. So here I am. I'm at a location, and I draw an R vector basically from the antenna out to here, right? So that's R. Well, do I have an A perpendicular? Yeah, absolutely, right? Because the acceleration is either that way or that way. R is that way, so A is definitely, no matter what way they're accelerating, A is definitely perpendicular to R. So what is going to be the direction of E radiative when it reaches our detector? The direction of the field. The direction of propagation is out, but what's the direction of E radiative? Parallel to the bar, right? Because it's got to be either this way or this way based on the direction negative Q times A perpendicular, right? Let's just for a moment imagine an electron accelerating in that direction, so in the positive X direction. And R is pointing in the positive Z direction. So when we get an E radiative here, that's going to point in what direction? Based on negative Q A perpendicular. Negative times a negative gives us a positive, and so it's going to be pointing in the positive X direction. So we're going to get an electric field pointing in the positive X direction. Well, what have I got inside this? What is this? It's a wire. What's a wire have? Mobile electrons. It's a metal wire. So what is that E radiative doing? Driving an alternating current. Driving an alternating current back and forth inside the wire and therefore inside the filament of the light bulb as well. Okay. Now it's alternating. How come we see the light bulb burning at a constant rate? How come we don't see it flickering? Say again. It's okay. For one thing, it's fast, right? We have a frequency here it's very rapid frequency. In fact, we can calculate in just a second. And even if it were slow, the light bulb heats up, right? And then it takes a while for it to cool back down. So, but it's happening so rapidly that we see sort of a continuous burning of the or brightness to the filament. Okay. So why does it go out? Okay, the acceleration, the radiation's this way. The radiation's oriented that way or that way, right? So how's that going to affect the charges in the wire? It won't drive it across the filament, right? It may, in fact, the acceleration may be that way and that way, but that's not the length we want. We want the acceleration along the length to drive a current. Yeah, look. What if I bent the ends of the wires? Let's see. Not enough. Let's see if we do more here. A little bit. I don't know if you can see it, but I can see a little bit of brightness, more than we had before. And it's also we angle. Okay, so what if we angle it? So here it's completely perpendicular. If I can rearrange it again. So I angle it. In fact, I don't even need that much angle. I don't know if you can, but I can already see. Can you guys see it burning a little bit? Yeah. And the more I angle it, the stronger it gets because I have more of a component along the axis that I want, right? If I go like this, then the component along the wire is 0. But if I angle it even a little bit, I've got some radiative field component. I sort of decompose the vector, right? I know it's that way, but I can consider a component along the direction of the wire, and I get some current. Okay. Why does it go out over here? It's on the same direction as the accelerating charges, right? No radiation along the direction of acceleration. Lift it up a little bit. Well, the other confound we start running into is that, remember, there's a distance dependence. So it's a 1 over r distance, and so if I start bringing it too far away, it starts to go out. Now along this direction, yeah, well, it's smaller because of what? The angle means I've got what? What's the direction of acceleration? That way, right? But the r is now that way. Yeah, you have a component that of the smaller a perpendicular component, right? A smaller a perpendicular component. Yeah. And I don't want to bring it too close. I could actually burn the light bulb out. And then back here, again, it's radiating in all directions. Okay. And so we have the same reasoning as we just had before. Okay, again, it goes out like that. And then over here. So, we've got at least a qualitative understanding of what's going on just based on electric fields, which is what we, day one of the course, right? But now that we know something about accelerated charges and how accelerated charges produce radiative electric fields, those radiative electric fields are just like any other electric field. They're going to cause charges to accelerate if we have mobile charges in their presence. Those accelerating charges, that's a current. And that current causes, through this tiny little filament here, causes our light bulb to glow, because the radiation is, that energy from the current is then being dissipated away as radiation of itself. Now here's a question. So the light bulb is bright, right? It's emitting radiation itself. Why? Why is the light bulb bright? Do we have accelerated charges? How are they accelerating to give off visible light? What happens? Not just vibration. Think about the model of what the charges are doing. Collisions, right? If you have a collision, you definitely have an acceleration because you have a charge that's moving and then comes to a stop. That's a big acceleration, right? That's a pretty big acceleration. Say again? They're not elastic, right? Because not elastic collisions, because that energy is then being radiated away as light. Okay. Questions here? We're not done with this model yet. We'll come back to this demo a little bit later. There's just a piece of terminology also we'll introduce that we'll come back to later. We have acceleration limited to one axis. So we have ERAD, a radiative electric field, could be only in the positive x or the negative x direction. Okay, it's not going to be up or down or any other component. We call radiation where it's oriented only along one direction, where the field vector is oriented along one direction. There's a special name for that. Anybody know what that is? What type of light is oriented? That's polarized, yeah. So this is called polarization or polarized light. And it's a different use of the term polarization than what we've seen before. We don't necessarily mean here a charge separation. We're talking about a particular orientation to the radiative electric field. The light you see ordinarily is typically made up of, you could have ERAD pointing this way coming at you, or that way, 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 or any number of combination of ways entering your eye. Okay, but if you can arrange it so that ERAD is only in one direction or along one axis, it's called polarized. In fact, in this case, it's specifically linearly polarized light. Because there are cases where you can have it polarized in like other patterns such as circular, which we won't go into, but linearly polarized light. We'll come back to that. Next time we will talk about energy and momentum stored in radiation.